Greetings, students. This is Mr. Allen, and today we are going to look at section 4.4, which is on the fundamental theorem of calculus, among other things. Making this video pretty early in the morning, so sorry if I look a little tired. So 4.4, fundamental theorem of calculus. The objectives today is to evaluate definite integrals using the fundamental theorem of calculus. That's probably the biggest goal. We also want to understand and use the mean value theorem for integrals, which is different than the mean value theorem that we've talked about previously. We want to find the average value over a closed interval, the average value of a function, and we want to be able to use the second fundamental theorem of calculus. The connection between the derivative and the integral was discovered independently by Isaac Newton and Gottfried Leibniz in the fundamental theorem of calculus. So those two gentlemen, there were lots of mathematicians that were working towards this thing called calculus, but those two men, most people know Newton a little bit better, were given credit for calculus because they basically connected the derivative and the integral. So let's not waste any time and get right to it. What is the fundamental theorem of calculus? The fundamental theorem of calculus is as follows. If a function f is continuous on a closed interval a to b, and capital F is the antiderivative of f on the closed interval from a to b, then the definite integral, that's what that's called, the definite integral from a to b of f of x is equal to the antiderivative at b minus the antiderivative at a. That is the fundamental theorem of calculus. You'll see me refer to it a lot of times as FTC. So here are some guidelines for evaluating a definite integral using the fundamental theorem of calculus. I'm going to leave that in here as part of the notes. But let's go ahead and look at an example. And again, I'm actually kind of leaving some things on here typed instead of writing, just so that it's clear. And I've noticed that when I write sometimes on the screen, it makes kind of an annoying noise. So I'm trying to not do as much of that. So let's say we wanted to evaluate the definite integral from 1 to 4 of 3 square root x dx. So we want to evaluate this guy. The first thing that we should do, or could do, is we could pull that constant factor 3 out to the front. Now the next thing that we're going to probably need to do is we're going to have to figure out what is the antiderivative for x to the 1/2. So let's kind of review our power rule for integration. So remember, when we did the derivative, we take the exponent, we subtract 1. I'm sorry, we take the exponent, put it in the front, and then we subtract 1 from it. So if we were doing the derivative of this, it'd be 1/2 x to the negative 1/2. That'd be the derivative. Okay, so that's the derivative. But what if we want to go this way instead? What if we want to integrate? So remember, what we did here is we pulled the exponent to the front and then we subtracted 1. So what we're going to do is just the opposite. We're going to add 1 to the exponent, and then we're going to divide by whatever that exponent is. So in this case, when you add 1 to 1/2, you're going to get that 1/2 or 3/2, and then of course you got to divide by 3/2. So this is indeed the antiderivative. And then we're going to evaluate that from 1 to 4. And that's going to give us 2 times the quantity 4 to the 3/2. So this is the b value. This is that b value for 4. And then, of course, here's the a value of 1. And so our answer here is 14. So that's the process of evaluating a definite integral using FTC. The mean value theorem for integrals. The area of the region under the curve is greater than the area of an inscribed rectangle that's less than the area. In other words, this area under this curve from A to B is going to be greater than, let's say, this inscribed area like this. It's also going to be less than the circumscribed area. It's somewhere in the middle. The mean value theorem for integrals states that it's somewhere in between those two. Here is the mean value theorem for integrals. It says if f is a continuous function on the closed interval from a to b, then there exists a number c, which is similar to our regular mean value theorem, such that the value of the definite integral, in other words, the exact area, is equal to this right here is a width and this is a height. So this right here is a rectangle. In other words, there's some rectangle that we could form that's less than the circumscribed one and more than the inscribed one that will give us the exact value of the definite integral. In other words, the exact area. I'm actually not going to do an example of this one. I'm going to leave that one for you to explore. The average value of a function. The value f of c given by the mean value theorem for integrals is called the average value of f on the interval. Here's what the definition is for the average value of a function. And before I give you that, suppose you have some function that's doing all this crazy up and down stuff. And we're going to go from a to b. Excuse me. The average value from a to b, so it goes all the way, let's say up here at this point here, let's say it's 10, and then its lowest point right here, let's say it's 5. Somewhere in the middle of those values is the average value of the function over that interval. Let's say it's 7 or whatever. So that's what this is doing. Now, please keep in mind, this is different than the mean value theorem, which I'll go back to right now. Notice that here we've got the definite integral is equal to the height of some rectangle with the width AB. Here, it's not an equation. This is just a formula for you to figure out the average value of the function. So it's the value of the definite integral, and then you're going to essentially divide by the width of the interval. The other way I always like to explain the average value of a function is if I said, how do you find the average, let's say, body weight of a group of 100 people? What do? You add up all of their weights, and then you divide by 100. That's essentially what we're doing here. We're adding up all of the weights, and then we're dividing by however many people there are. So this picture here is kind of what I was trying to illustrate in that last one. So let's find the average value of the function f of x equals 3x squared minus 2x on the interval from 1 to 4. So that function, which is parabolic, is going to probably go up and down. We want to know what's the average value. So all we're going to do is we're going to just plug it into the formula. So here's our formula. We know that a is 1 and b is 4, so that's where the 4 and the 1 come. That's where the 1 and the 4 come from. And then you just plug the function value or the function definition in there for the function. So f of x squared, I'm sorry, 3x squared minus 2x. Now we need to evaluate the antiderivative. I'm going to go and clear off my writing here. So the antiderivative of this, remember, you add 1 to the exponent, and then you divide by the exponent. So you'd be dividing by 3, so the 3's would cancel. Now I'm doing very easy integrals in this lesson video because I don't want to get hung up on that, but that's something that you need to review. I've just done a couple of examples using the power rule. Again, we're going to evaluate this integral from 1 to 4. And we keep going and working it out. And it turns out that the average value here is 16. So this function at its lowest point, which was at 1, 1, is way down here. It's parabolic. At its highest point, it's up there at 440. The average value of this function turns out to be 16. Okay? That's the answer. Okay, the second fundamental theorem of calculus. We're almost done. We got to talk about a couple more things here. The definite integral f on the interval AB is defined using the constant b as the upper limit of integration. X could be used as a variable of integration. This is how we're going to use the second fundamental theorem of calculus in most cases. To avoid confusion of using x in two different ways, we're going to use a temporary variable t. So a lot of times, in fact, let me just show you what I mean. If I'm going to integrate from, let's say, a to b, where b is a constant of the function f of x, I could change that b to an x, but then I need to temporarily change the variable of the function to t. Now, you might be asking, why in the world would we want to do that? Why would we want to make such a crazy substitution. The reason is consider, let's say I'm going to integrate the function cosine x, but I have to do multiple integrals, okay? Multiple integrals. So for example, you could evaluate 5 different definite integrals, one for each given upper limit. Or what you could do is you could just use the fundamental theorem of calculus part 2 to just do the integration once and then just evaluate. I don't know if that makes sense. Let me say that again. When you do it this way, you're only integrating once, and then you're just using evaluation to get your answers. So what we've got here is the following. Well, let's look at the work. Okay, so we've got 0 to x cosine t dt. What's the integral of cosine t? Okay, so here's a non-power rule one. Well, it's sine t. And we're just going to evaluate that from 0 to x. Well, that's going to be sine x minus sine 0. Well, what's sine 0? Well, that's 0. So it's just sine x. Now what we can do is simply evaluate all 5 of our values at sine x. So I'm telling you that the area under this curve from 0 to 0, well, of course you already know that one, that's 0, right? From 0 to 0, that's going to be 0. So when you do the sine of 0, you're going to get 0. But we already knew that the area from 0 to 0 is 0. That's one of our properties. If I want to do pi over 6, I just evaluate sine of pi over 6, which is 1/2. Pi over 4, radical 2 over 2, etc. The function capital F is accumulating the area under the curve of the function cosine t from 0 to x. For x equals 0, okay, these are the same things I've kind of said. So this is an important concept in calc, and that is that integration can be used to model an accumulating function. Another way we could write the fundamental theorem of calculus is as follows. The derivative of the definite integral from 0 or from a to x, where a is a constant, is simply the value of the function at x. So for example, if I wanted to do the derivative of this, integral from 0 to x, square root of t squared plus 1, only thing I need to do is just plug it in. So it is just change this t to an x and you're done. By the way, this 0 could have been any number and it would have given us the same answer. But we got to be careful, if I will remind you, is if this isn't just x. If that was x squared or something like that, then that changes the answer using something called the chain rule. All right, I'm going to kind of jump to this net change theorem. I also will refer to this as displacement. So the definite integral of the rate of change of the derivative of the antiderivative gives us the total change of the net change of a quantity. So let's look at an example of that. So let's say that a chemical flows into a storage tank at a rate of 180 plus 3 t liters per minute from 0 to 60. Find the amount of chemical that flows it throws into the tank during this first 20 minutes. So what we're going to do is we're going to let C of t be the amount of chemical that flows through the tank at time t. Maybe C wasn't a good idea for me to use because that kind of seems like a constant. This is not a constant. We're using C to represent chemical. Then C prime would represent the rate of change. So here is what we're talking about. If we want to know the amount of chemical that flows through the pipe in those first 20 minutes, so we got to do the antiderivative of the derivative. Well, what is the antiderivative of the derivative? Well, it's the function itself. It's 180 plus 3t. Okay, so this is the rate. That's what we're given here. That's the rate right there. The rate of C prime, the rate of flow is this 180 plus 3t. So we just need to integrate that. So we integrate the 180 and we get 180t plus 3 over 2t squared. And we'll get an answer of 4,200. So this is a nice application of integration. They gave us the rate at which the fluid, the chemical was going through the pipe. Therefore, we can just do the integral of it to evaluate how much total amount went through. So this is how much accumulated after that first 20 minutes. Now, please keep in mind that that displacement, there could have been some chemical like coming out, and then maybe there was some a little bit going in, but more coming out. Overall, there was 4,200 units of chemical, right, that came out over those 20 minutes. We don't know. There could have been some at some point where the level of chemical was going up and then coming down. It could have varied, right? So this is what we call displacement. When we want to know from the beginning to the end, how much did it change? How much was displaced? Okay, so that's how we get this. For the total distance traveled, this is going to be a different concept. Here we're going to take into account, oh, they went forward, let's say, but then they went back. And now you may have only traveled 20 miles, like 20 miles displacement, but you actually may have traveled 30 miles because you went like, 40 miles ahead and then 5 miles back and then 5 miles forward or something. You know what I mean? So in order to deal with total distance traveled, we have to do the absolute value. Guys, we're at 15 minutes. I did not think it would take that long. Sorry. Have a good day.